Research cyber infrastructure here at UH Manoa. So I work with Dr. Sean Cleveland, and he's bringing me on to build a bunch of RAG systems, some chatbots for various domains that he's working with or projects. And then I'll show a little bit of demo of the projects that I'm working on. So just to give you guys an idea, on the right side here, I have, according to this article, some of the big companies who have been using some sort of RAG implementation or architecture into their system. So Google DeepMind, AWS, Hugging Face, Claude, Meta. So this is a hot topic that a lot of companies are using. I was surprised OpenAI wasn't on here, but I'm sure they're using RAG on their backend. Yeah. Okay, so first we're gonna cover just some problems with large language models to see like the motivation for why you would use RAG in the first place. And then we're gonna go into like the core concepts of RAG just to get maybe some of the terminologies right. And then I had you guys download a Jupyter notebook that was sent out yesterday in your email. And we're gonna go through step by step how to build a RAG system, just the basics. And then I'm gonna have like a hands-on RAG competition to see who can build the best RAG system. I have some template code that you guys can play with. And then the ending, we're gonna do some advanced RAG techniques. So once we cover all the basics, then hopefully you guys built up some of the knowledge to understand some of the things that you can update or change to make RAG systems better. And then I'm going to share some of the experiments that I've been running on my own time. And at the end, I'm going to ask you guys to do an evaluation survey on the workshop. I'm going to have a QR code for you. Okay, so I was going to ask this question, what are large language models good at? But I'm sure, a lot of you guys know how good it is. Like how many of you use large language models in like your workflow, like ChatGPT? Yeah, almost everyone. So I'm gonna yeah. Um, so yeah, it's good at a lot of things. It solves most problems out of the box. It can help you with coding, rewriting text, fixing your grammar. I know I did that a lot in my PhD dissertation. It has a lot of general knowledge about almost everything. You can show it even images, which some things are hard to describe in text. You can just show it an image. It's good for brainstorming, explaining concepts. Yeah, as I said, writing assistance, learning support. So I use this a lot in my learning. I'll read whenever I try to implement something new, or learn about a new tool. I'll read a bunch of research papers, and then anything that I don't understand or have a little bit more questions on, I'll just throw it into ChatGPT just to make sure I understand what I'm reading. And also prototyping. Okay, so maybe I'll ask this question. What are large language models bad at? But think of this in the early ChatGPT phase where because as I said earlier, OpenAI probably has some rack system on their backend. So maybe think about what could it not do in like 2022, 2023. Huh? Math? Okay. Providing accurate answers, maybe hallucinating. Logic? What do you mean by logic? Okay. Maybe like um it's just doing pattern matching or just not reasoning very well about Anything else? Can't think of anything.
Anything that happened after they were cleaned.
Yes, that's a good one. It was only trained on things, or it only knew events up to when it was just trained on. Okay. Well, here's the list. It, of course, we said that it might generate inaccurate answers, hallucinations. It didn't have access to new data. It only had data that it was trained on. It wasn't really specialized into anything. It had like a general knowledge of how to do a bunch of things, but once you get into maybe like something you wanted to focus on, it had a trouble time doing that. And it's not able to reference where it gets its answers from. And it has a limited context window. So if you have maybe like a 200-page research paper or a bunch of research papers, you couldn't just, throw it all into ChatGPT and have it expected to understand everything. It can only understand whatever context window it was trained at. Okay, so what is the solution? So what if I told you could instantly search through every academic archive or climate report or financial data, Hoy reports, plant species Hoy, and get a precise, accurate, cited answer in seconds? That'd be pretty cool, huh? The answer is, or the solution is to use RAG. The RAG can help you accomplish this, which stands for Retrieval-Augmented Generation. So this is the naive basic components of how a RAG system works. You have, let's start from the top left, right here. So you had, a bunch of documents. Maybe you're in biology and you have all these documents about like a taxonomy. You have all your animals and the food chain of how everything works. Each animal has their own document. So imagine each one of these are just one paper on each animal. The way that RAG systems work is that you go through a process of converting these documents into a embedding, which is a numerical representation. It's a number. And the number has some meaning associated, semantic meaning associated with the document. So if you had something like a monkey and a orangutan, since they're similar, they would have numbers that are very close to each other. So like 2 and 3. But if you had something like a giraffe, which is very different from a monkey, it'll be given maybe like I don't know, 97. And then once you store all of these numerical representations of these documents, you put it into a database. At this point, the way that you would have a large language model understand your documents is that you would just give the whole database to the AI. But we want to focus or filter the large language model on a subset of those documents. So what they do is when a user asks a question like, what animals eat bananas or something, it goes through each of those animals, those documents, and maybe some of them mention something about like bananas and maybe they like potassium. And then it'll figure out what document is the most similar to my query. And then you can add like a parameter to say, I want the 3 closest animals that eat bananas. And then these are your 3 documents. And you put that along with your question, and then the large language model comes up with the answer with those subset of documents. That makes sense? Yeah. Okay. Okay, so here are the basic components of RAG. You have your indexer, which is how you're going to store these documents in the database, right? You have your retriever, how you're going to get those documents out of the database, how you're going to filter them, and then generation. How are you going to tell the language model to use these documents that you filtered to answer the user's question? But also, this is a data problem. So you also, a lot of what you'll find online is they don't talk about data wrangling. So you need clean data. So data acquisition, where are you getting your data from? Is it correct data? You also need to do some pre-processing. So if you're fetching data from like a web page, it could be very messy, has HTML all over it, which doesn't help the model. Some models, I think it helps, but I think most of the time you can get rid of that and just put the text. And then enriching the data, how can you maybe add more or re-represent the data in a way that's maybe easier for the language model to understand. So maybe if you have like a list, HTML list, where it's like just listing things, maybe you can turn those into sentences or ask the language model to read data that you scraped and then represent it differently. I'll get into how you can do that later in the presentation. And on top of that, once you've built this whole system, how do you evaluate it? How do you know if it's correct or not? So we're gonna get into a little bit of that too. Okay, so these are the chat systems that I've worked on. This is free to use. Oh, this top right one is it's called a policy bot. So I got the frequently answered questions from UH. No, sorry. There's a website where you can access all the policies on UH system-wide. I built a scraper that got all the information from that website. And then I put it all into a RAG system. So then you can ask the AI questions about UH policies. The policychat.its.hawaii.edu. You can ask, what is a whistleblower? Okay, and this is a whistleblower is an individual who makes a good faith report or indicates an intent to make a good faith report or what is perceived to be a good faith report of misconduct by a member of the university. And it comes back with a source of where it got that answer from. Whistleblower and retaliation policy. This other system that I'm building for, so I'm working with the state of Hawaii on their finance department, and they have a bunch of these bills that are amended, or they have to figure out the budget to, I guess, address the bills that are coming out. And they have, this budget, they have all these bills, they have all of these laws in Hawaii that they need to abide by. So right now I'm building out a system that knows how to access a bunch of these databases of documents. It's not fully flushed out. I'm still working on it, but you can ask questions like, what is the budget for, education and how would that impact the future state of Hawaii? Maybe I'll be. So right now it's not really optimized. This is when I first got onto this project, this was the first rack system that I was building, but I know how to make it a lot better now. But it comes out with this long information explaining about like understanding Hawaii's budget, education, and then goes into the overview, and then budget size, what the budget is spending money on, like facilities, maintenance, capital improvements, and so on. Workforce development, economic diversification, and how does that impact Hawaii? Yeah. So it pulled out 747 sources for this, that's not how you're supposed to do it, but it's an example of what not to do. And then Hoku is another project that I worked on a little bit. It's you can ask questions about UH system policies and also ITS frequently answered questions. Yeah. Okay. So now we're gonna go into the interactive notebook. So if you have it open, you can run the code cells along with me. If you don't, maybe share with the person sitting next to you, but I'm gonna have it running on my computer as well. Okay. So just run the first cell. Can make this bigger. Looks okay. Okay. So we're just gonna load a bunch of libraries, and then we're gonna load a embedding model, which is, like I said, how you're gonna turn those documents into a numerical representations. And there's a bunch of different embedding models you can use. There's Gemini, there's OpenAI embedders. And there's also embedding models that have been trained specifically for like financial documents, law documents. So this is just a general purpose sentence embedding model. So it's been trained on embedding sentences. The tokenizer and the I want to say this is a large language model, but this is a small one. So maybe it's a small language model. It's a SLM. This is what we're going to be using because it's going to take a long time to download the language model. And you guys, I don't know if everyone in here has an OpenAI API account or API key. Okay. So the first thing we're going to get into, that's also, it's not super important, but it's useful to understand how these embeddings work. It's called tokenization. So tokenization is how you break documents into subunits. And there's different ways you could do this. You could split, say you had like this long text document and then you want to embed it. You can't just embed the whole thing into a single embedding. You need to, split it into groups of what you wanted to embed. So you can do character tokens, which is just getting each individual character and turning that into embedding, which doesn't give you a whole lot of information because you're only having like 26 characters and whatever symbols. It's not a very good way of putting information into a numerical form. You could do word tokens, so splitting by spaces and just turning into words. Sentence tokens, which is what this model here was trained on. GPT does something called byte pair encoding tokens. So they have their whole algorithm on this website. I'm not gonna get into it, but it's basically finding frequently mentioned characters that occur very frequently together. So they scraped a whole bunch of data. They found all the characters that were that frequently occurred next to each other. So maybe, I don't know, like the th maybe occurs a lot in the human language. Um, and they do that to get like a little bit of balance of between, getting a word in token or a sentence token. And that balance, um, it allows them to, I guess, have like a finite vocabulary for the model, and having also an understanding of what people are trying to say in human language. Okay. But for the purposes of this workshop, we're going to be doing sentence embeddings. But also, I'm just going to give you a quick breakdown of what word embeddings are, or like how to kind of ingrain what these text embeddings are. So again, if you took the word embeddings of words that have very different meanings are very far apart numerically in this embedding space. So king and banana are very far apart because they don't have any related meaning. King and queen are going to be very close together because they both deal with like royalty. Man and woman will be together because they both deal with like gender, right? And then another cool thing that really surprised me when I first started learning about all of this is that, say you had king, which was assigned maybe the numerical representation 2, you took queen, that was assigned 3, man, that was assigned 82, and woman, that was assigned 83. How was it? What do you do? You take king 2, subtract 82, that gives you negative 80, right? And then you add woman, which is 83, and then you get 3, which is queen. So they have the same distance apart. I found that pretty cool. Okay. Yeah, so in this workshop, we'll be doing sentence embeddings. So this code cell, we have a set of questions. What is the capital of China? And explain gravity. Say those are your questions that the user is asking. And then you have your document, which is this document here. The capital of China is Beijing. Gravity is a force that attracts two bodies towards each other, and it gives weight to physical objects and is responsible for the movement of planets around the sun. Okay. So we're going to split these documents into sentences. We're just going to name that documents here. And then that embedding model that we loaded earlier, we're just going to turn those into a numerical representation. And you do that through embedding model.encode. So now you have your query embeddings, and then you have your document embeddings. So the capital of China is Beijing, and then gravity. And then we're going to compute the similarity between the queries and the documents. So this similarity is doing like something called cosine similarity. So it's finding the angle of how different these two embeddings are apart. So for this first sentence, what is the capital of China? It's going to find the here the distance away from this sentence, and then explain gravity is going to find the distance. Oh, sorry. Sorry. What is the capital of China is going to find the difference of the distance between these two sentences, and then the same for gravity. And this tensor has those differences. So, oh, sorry. Maybe just to make this sound easier, the higher the number, the closer the distance is. So China, what is the capital of China, is very close to this first sentence and very far away from this second sentence because it got a lower score. And in the second sentence, explain gravity, got a lower score for the first sentence and a higher score for the second sentence. Okay, that makes sense? Okay, so now we're gonna try to get a bigger piece of text. So they have this website here that's freely able to be scraped. I'm not gonna have a bunch of documents. This is just a story about Moby Dick. I'm not gonna have a bunch of documents because it's gonna take a long time to process everything, but imagine this is a very large document. And then I have some code in here that you guys could use or experiment with. It's called AI crawler. The way that I'm using it in this code block, you give it a website that you want the crawler to grab information from. And then you can define number of workers to make it faster, but you can also describe something called number levels deep. So if you gave it like the Amazon website, it'll grab all the text from that initial website. But if you have a 1 here, it'll find all the links on that website, visit each of those, and then grab all the documents from each of those links. And then that's your database. If you're going to do this for web page scraping. And then I have some other stuff in there for like if you want to do like AI. So I think if you give it an API key, you can describe a prompt of how you want the crawler to grab information for you or grab certain parts of the information. But that wasn't heavily tested. And of course, it's using language models. So you can use it at your own risk. Okay, so this is the document that we grabbed using HTML to text, which just cleans out the HTML, just turns it into text. So this is an example of like the best case scenario. Like you have a data set that is just strictly text. But when you're scraping data, you're gonna run into a bunch of issues. There's going to be tables, images, HTML everywhere, garbled characters, and like lists that you don't know how to handle. So, and depending on where you're getting your data from, you might need like your own special formatter just for that website. There's tools out there that try to do like a catch-all, but it's very hard to find a website that matches perfectly. So these are some of the tools that you can use. So Camelot and Marker, which is a GitHub public repo. I found that they're good for parsing tables. This Marker tool is good for parsing research papers or tables and research papers. PDF Miner and PyMu PDF are good. From my experience, they're good at parsing PDFs. There was a research paper that I read that had PDF Miner to be like the best catch-all for scraping most PDFs. But that paper also found that in certain documents might be easier to parse with other tools. Yeah, I'm gonna get into that list later too. And we have Beautiful Soup and Scrapey, which are HTML scrapers. So that'll help you build your own web scraper. Okay, so now we're gonna go into like the basic components of RAG. So again, it's indexing, it's retrieval, and it's generation. So indexing is how do you split your data into chunks? So now you have this long document, the Moby Dick, as we had earlier, right? You can't just put all of this in a rack system. You have to split it up. So that's called indexing. And then the first question you might ask is how do you split it into chunks? For here, we'll just do a 200 chunk size, and then I'll have you guys experiment with, different chunk sizes. And I think at the end, I'll have some research that explains what is like optimal. But for now, we'll just do a 200 chunk size, and then we'll split this here. We'll say, give me for that text that I had earlier, we're going to split it into characters of, 200, and then print those chunks. So this is chunk 1. This is chunk 2. All right. One thing that I also have to point out is, since we're using a sentence embedding model, doing it this way isn't optimal. You might not have the best results because, look at the sentences. They're not even split by sentences. Like Perth is a name in the document, and then you're splitting it. So the model, when you put all of this into a RAG system, it's not going to have all of that information. It might lose very important, um, ideas that you have in your document. So keep that in mind. For now, we're just going to operate and keep it super simple on, just doing like a character chunk size, not by sentences. Okay, now we have our retriever. How are we going to retrieve those chunks? So I have a question here. What physical impairment did Perth have, and how did that occur? So from what we saw earlier with the China sentences and the gravity, we're gonna turn this query here again into an embedding. We're gonna get those chunks, turn it into embeddings, and then we're gonna compute the similarity between each chunk. And then, yeah, here I print it, and then I have the highest rated chunk right here. Oh, sorry, this code prints the highest rated chunk, and then I also print the lowest rated chunk just to show you guys which chunk it found like the most similar. So here are all the similarities between the query, and then the highest similarity was this chunk, and lowest similarity was this chunk. So the question was, what physical impairment did Perth have, and how did it occur? The most similar chunk, what I think that it found was this is the loss of extremities of both feet. So that kind of answers the question. Those both have like similar words in it. That's probably why it got a higher similarity score. Whereas this one didn't really talk about let's say physical impairments, or those have those kind of words. Did I run this? Okay. And then now that we have the highest rated similarity chunk, we're gonna tell the language model to generate the answer. I'm not gonna go into this code because this is using the Hugging Face model, but I'm sure a lot of you guys have API keys or access to like large language models. So I think here and where was it? Oh yeah, here and here, I'm gonna print how the language model would answer those questions given the highest rated chunk and the lowest rated chunk. So the answer for the first highest rated chunk was the loss of extremities. Sorry, here's the question again. What physical impairment did Perth have and how did it occur? The loss of extremities. And then the lower rated answer, the chunk that had a low similarity gave this answer. And I also asked ChatGPT to answer those questions for confirmation. And then in fact, oh sorry, the answer was Perth lost the extremities of both feet. So now we went through the whole basic components of RAG. Okay. And this is much simpler if you use a large language model like OpenAI. You would just send your question along with your context, and then you get your answer. And this is the code of how you would use it.
So did the generator know to put chunks back together that like split words and stuff like that?
No, yeah, that's the key point here, I guess. So you're in charge when you're building these systems, you're in charge of making sure you split it properly and it's being handled by the language model properly. Oh, yes, question?
Like the compared to the ChatGPT one, it's like it's not a complete sentence answer. So you force it to be a complete sentence, or is it like
Yeah, so that's the generating part. From here, I mean, this is also using a smaller language model, so it doesn't have the more capabilities like OpenAI. But you would use prompt engineering techniques or describe to the language model exactly what you want it to do, how long you want it to make that answer, or answer this in complete sentences, or sometimes it gives you too much information, right? And you say, just give me a one sentence answer or 2 words or something like that. Yeah, so that's the generating part. So each one of those, indexing, how are you gonna chunk the data? Retriever, how are you gonna retrieve the data? And generation, how are you gonna generate the answer? Yeah. Any other questions? Okay. Oh, wait, is there anything online? Can you share the link? Um, oh, you did. Okay, okay. Okay, so here, I kind of just like all this logic. So now you can, so now you can just give it your question and have, or give it a question along with the chunk, and then it'll generate the answer. So there's something called ChromaDB. ChromaDB helps with managing all of these chunks. And there's different services, cloud services, that help in managing vector databases. for example, ChromaDB, it's kind of low level as opposed to a lot of these cloud vector storages. So this is the code to store these embeddings that you had earlier into a vector database. And then you can also store like a metadata along with it. Right now, I'm just naming the sources by the chunk name. And then you can give it an ID, and then you give it the chunk embedding. So this helps with like, I guess, organizing your chunks that you have in the back end. So maybe you have like different collections. So the way that you can create like groupings of embeddings on the back end is ChromaDB calls it collections. So this, I have one collection now, but imagine if you had, you know, for example, the finance project that I'm working on. I have the bills, I have the laws, I have appropriations. You have maybe some statistics about people living in Hawaii. Each one of those can have its own collection. And then you can devise a system that accesses these different collections based on what the user's goal is, right? So you're kind of like focusing the model into, like each one of the, or you could, the new thing now is multi-agentic AI. So you could have maybe like a chat on, each of these different collections, and it's like an expert at each of these collections. And then you have your chat on top, this agent, this facilitator that talks to each one of these agents and, you know, discusses with them to see what is the right answer for the user. Okay, so now we're gonna query the collection. So in here we just defined one collection, and we had a bunch of different chunks. We're gonna encode my query. Again, this is all very similar, and then you're just gonna call collection.query, and you're gonna say I want the highest rated result. Just give me one answer. And again, it was the same answer that was given above, the loss of extremities. I don't remember if I ran all of this. Okay, so another thing too is these cloud vector databases, what they also help with is if you have a lot of documents, if you guys know things about like how databases work, storing all your data into one database is maybe not optimal, because you would tell, say you had a question and then you had, the system on the back end, it had to compare your question to each one of those documents. So it's an order of n. But if you break up your databases into different databases, you can kind of structure how the backend works to reach like a cache, something that's frequently used. So maybe there's this database that's I don't know, like closer to the user, or they have a very fast, like GPU on it that does those calculations. The cloud storages handle all of that for you. So that's one of the benefits of using that. It's stored on your local computer. Yeah, ChromaDB is, everything's stored on your local computer. Yeah. This is more like low level. If you were to build a cloud storage for other people, I think you would use maybe a ChromaDB internally and then expose that to everyone to use. Okay. Now we're gonna get into evaluations. How do you know what you're building is actually correct? The best case scenario is that you guys have a labeled data set. So something like frequently answered questions is like the perfect database for a RAG system because everything's formatted the way that a RAG system would work. So if I click on one of these questions, these answers are your documents. Okay. And then these questions are your evaluation questions. So imagine you use my scraper, you grabbed all the questions or all the answers from each one of these documents, and then you chunked it by, again, like 300 or say that you found the optimal chunk size. And then now you have your question attached to what document that question should retrieve. Does that make sense? Yeah. So that's the best case scenario. Oh yeah, and then this is just running through answering one of all of those questions that I have here. Your second option is to use something called large language models as a judge. I thought that this wasn't a good idea, but until I read this paper here, judging large language models as a judge. And what they did was they compared the results of a large language model annotating answers from other large language models. So it acted as an evaluator. And then they did the same study with humans. And they found that humans and the large language models graded the papers very similarly. So it could be used as a potential evaluator for certain documents. But it also depends maybe on like how specialized those documents are. Maybe you have like this very special field where this expert has more knowledge of the area. So then you would, in that case, then the expert would have would be the better grader. But it could be an option for you. And this TrueLens, this is another library that you could use. So on deep learning AI, Andrew, I don't know how to pronounce his last name, but it's NG, and Andrew Nung. You guys, you guys probably have seen this guy if you, I don't know how to say his last name, but this guy did a collaboration with Anupam Datta on evaluating answers from large language models. And they have this library that you can use. And you can read more about it, I guess, in the Jupyter Notebook that I share with everyone. But they have like these three things that they evaluate the model on using a large language model, which is the answer relevance, context relevance, and groundedness. But you can read more about it in this paper, this article. A third option is to use a synthetic data set. So basically, you just ask the language model, you give the language model a bunch of these documents, and you say, what questions can you ask to answer with these documents? And then on the second pass, you give the language model that same document, and then the question that it told you, and you say, answer the question. And that's your data set. Right? Okay, and then the fourth option, the fourth option is through experimentations. There's these popular data sets that have been published. They've been used a lot. Hotpot QA, Natural Questions Squad, Trivia QA. So this, you can do your own experiments to see generally what would work. But also there's a lot of people doing research in this area anyway. So there's probably a paper published about it. So you can just do like a quick Google Scholar search to see if they've what question that you're asking and if it's already been answered. Okay. So this part of the workshop, I'm gonna have you guys do some experiments on your own. If you don't have it working on your computer, maybe you can ask the person sitting next to you, or I can answer any questions that you have while you guys experiment. Um, so this part of the code, I have like this template to, it already builds the whole pipeline of a Chroma database. It's using the document that we fetched earlier about Moby Dick. And then you can specify the chunk size. You can also specify overlap. So yeah, that's another thing too. And when you're building these, the indexing part is you don't need to have a hard stop at, the chunk size. You can do a little bit of a overlap. So if you had, a document that was like this, and then say your chunk size was 200 and it was right here, you can have an overlap. So instead of doing this, you would capture a little bit of what was in the previous chunk. So then you're not losing this little, like this area here that would have been an issue. You're kind of addressing it by capturing this whole chunk instead. Okay, that's the chunk size and the overlap. This is how you use the code here. Chunk size, overlap. And then I have some embedding models from Hugging Face that you can try and experiment with. The tokenizer and the large language model you can use here, but make sure if you change the model out, you use the same tokenizer from the other part. Okay. So I'm gonna have you guys maybe run through the code, change the chunk sizes and the overlap, and then we'll see who gets the best. Oh yeah. So I have our results here that you call after you create this retriever, evaluate Q&A set, and then it'll give you an average similarity score between like the answer from the large language model and what the expected answer is. Any questions? Did I skip anything? Okay. So maybe at what time does this end? I want to save 20 minutes by the end. So 12:40. Yeah, I guess you have like 14 minutes to run this. If you guys have any questions too, I can answer it. So maybe we'll do it like this. If you get a better score than 0.31, then I'll write it up and we can see what's optimal. The prize? Sorry, I don't have prize. You can get one Hershey's kiss. Still, but Mhm.
I think I was trying to run these, and then, and I slowly started running everything again, and now it's kind of like it's.
once you can. I think this part of the code. You have to delete the collection. You can do yeah. So I think you can call client that delete collections. So copy from the period on, yeah. And then scroll back up. Yeah, there. I think before you create it, then you can delete it. Client dot delete collection. Change the name. Oh no, sorry, of the other one.
But how can you delete something if it's not, was it created? Idiot?
Yeah, so I think when you ran all your cells again, did you run it the first time?
Yeah, because I was skipping cells, so then I got the triggering error that it was missing stuff, so then I decided not to run them individually. Okay.
Yeah. Oh, it ran.
I don't have the little bar thing. It complained that I didn't have that package.
Oh, okay.
So then,
Yeah, it's working. Yeah, so if you run into issues with like a collection array existing on the back end, then you can call this. So client is like your ChromaDB database, and then you just delete the collection before you create it, because you can't have two of the same collections on the back end.
like, it's not in the same folder as this code.
It's in Docker. Yeah. Hmm. Maybe I'll do a little test. So I increased the chunk size and then the overlap. So I got with the higher chunk size and the high overlap, I got a better score. So yes. Huh? Oh, I'll try to scroll up. The only other thing you can do is to rebuild the document. So, I always this.
Code embeddings.
Hmm?
He worked with, code, like computer code. Graph. But instead of, like natural language.
No, I haven't. I'm sure it's the same. So do we just change the embedding model? I'm sure there's a lot of different stuff we could do because I think about like how they chunking.
Yeah.
Okay.
I haven't tried to do it.
Yeah.
I'm reading a little bit now.
But, I mean, I think wait. Oh, we usually like optimization, like, increasing all machines, right?
Yeah, well. Sometimes.
Yeah, I guess it depends on what we're trying to do. Yeah, but I
So, well, it's. It should be, that's an alt, you know, font. It's supposed to do it, but people treat ones, right? So we're gonna do pass. Everybody gonna pass that. Your doctor's fine.
I am.
That would be really good.
So widgets.
So if you're running,
Maybe. Let Maya see if that fixes it, I guess. The guy next to him said that's what he ran into.
if you're running into issues, maybe with the imports on the first cell, it might be complaining about a loader. You can get that by adding this to the Docker file, hyphy-widgets. Okay, so it's anyone got better than what he did? Yeah. What score did you get? 2.4. Okay, so slightly better than this score. Yeah. What sizes did you use? Oh, 80 for the chunk size and 20 for the overlap. Yeah, so see, I scored better by just increasing the chunk size just a little bit. So I did 40. And you increased it by, 2 times that, or right? And then you got a lower score.
1.42.
1 point?
1.42.
1.42. What did you use? Oh. Reduce the chunk size. Oh, okay. So you got better results reducing it.
Yeah, right.
See, it's all you got to do your own experiments. This is why this is, machine learning. There's no catch-all for I guess, the model that you're building. So it's good to do these experiments. Okay, so now I'm gonna run through the last half of the presentation, which is getting into the advanced RAG techniques. So now you guys know the basics of how these systems work. Then you get into this questions of like what for your indexer. What are all the different ways you can store the data? How do you chunk it? What overlap do you use? How can you re-represent the data? For retrieval, what are all the different ways you can retrieve the data? So we only looked at something that's called a dense encoder retriever. So we found a cosine similarity between embeddings. But you could also use something called sparse encoders, which they have something called BM25, which is they have their own formula, but it's using like term frequency and inverse terms of documents that you have. You can read more about it, BM25. We're also looking at comparing the questions, the user's questions to the documents that are stored on the backend, which, it isn't the best way to retrieve those documents. So they have something called hypothetical document expansion. It sounds like something you hear from an anime, but you would ask the language model to hypothetically answer the question that you asked it. Because if you think about it, the answers that you're storing on the back end are in the form of an answer. You're right now, the way that if you would use the user's question, you're searching for questions. But if you tell that model to generate an answer, now how you're searching on the back end is more representative of what the user wants. And then generation. So on top of retrieving all the data, there's something called, what are the different ways you could generate the answer? Like I said, you could use prompt engineering. You could use chain of thought reasoning. You could use tree of thought reasoning. So there's a whole bunch of different ways to generate the answer. You could use reranking, which is also found to be very effective. Reranking is a specialized model that takes, so say you asked a question and then the retriever brought back a bunch of chunks. You have a special model that looks at each one of those chunks and compares it to the answer and puts the highest rated answer to the top. So they have their own re-ranking model that does that, especially for that. And then data wrangling, all these questions here. So now, for the research part of this, I'm just going to go through all the research papers that I've read on addressing these things. And then if you have these questions, you can just do a quick Google Scholar search and then try to find the answer yourself, and then do your own experiments on your own time. Because as you saw, it might not match. The things that you see on Google Scholar may not fit your specific data set, but it gives you like a general idea on what you should do. So for data pre-processing, if you're, say that you want to grab all this data, now you have to process it. This study, a comparative study of PDF parsing tools across diverse documents, did a comparison between a lot of the different PDF parsing tools and table parsers they looked at research articles and some financial documents, and then they compared which one of those was the best. And as I mentioned, PDF Miner was like the general catch-all for being good. For indexing, so what is the best optimal chunk size? This paper found that smaller chunk sizes work better. And large language models, what they found is that they only utilize around 40 to 50% of the context window. So something like Gemini, it has a million tokens. So remember what I said tokens, right? So it has a million, you can fit a million tokens in there. The optimal is right around the middle. So anything past that, oh, sorry, it's not optimal. It couldn't answer anything past, using the half chunk size. But again, smaller chunk sizes is better to get it to look at where you want it to. Long context RAG performance of large language models. So they did a comparison of, different chunk sizes, and they found that as you make this chunk size bigger, the model's performance of answering the questions that you give it decreases. But I know I gave Gemini as an example, but Gemini was actually the exception. So Gemini performed consistently as you increase the chunk size. So if you wanted to use a language model and you had documents that are very long, you would probably want to use Gemini. But anything else like Llama, GPT, and Claude, and Grok, I think as you increase the chunk sizes, the RAG performance decrease. For retrieval, the chronicles of RAG, the retriever, the chunk, and the generator, this paper talks about all the different ways you could retrieve the data. So this is where they talk about like reranking and sparse encoder, which is BM25s. They also did this pretty interesting experiment where they varied the answer within the context that you gave it and how that affected the model. I don't think it gave significant results, but you could read about it in this paper. Oops. More on the retriever. So this paper blended RAG, improving RAG accuracy with semantic search and hybrid queries. They did a comparison between all the different retrievers. So they did sparse encoder retrievers, dense encoder retrievers, and then basic keyword search. And they found there was no one best solution. It was, or actually the solution was one that was a hybrid of, I think it was a sparse encoder and a dense encoder. Which sparse encoders is BM25, and then they have their own formula that you can look at. Dense encoders is what we used in this exercise. Enriching the data. So how do you represent the data? So there's this thing called knowledge graphs. So knowledge graphs are pretty interesting. It's instead of chunking the data raw form, you would re-represent this chunks into entities and relations. So it's another way of like creating like simple units of your text. And then if you simplify it enough, it's easier for the AI to understand like how certain things are connected. So imagine you had something like you had like president, and you had like all the different presidents here. And then, each one of these entities, these nodes are connected to other nodes. So you could say which president has, I don't know, which president is a Democrat? Joe Biden's a Democrat, right? Okay. So then it would be like, oh, okay, what's the presidents? Let me get all the presidents. Now let me see which one's a Democrat. and then it'll find all of those. This paper here on the left is kind of like the motivation for RAG. So the more noise you give the model, it decreases performance. So that's why RAG it's good in the first place. This paper here, data acquisition. So this skipped the whole indexing phase and just use the retrieval APIs from other websites. So they just gave the model like the API documentation, and then it knew how to fetch information from all these different websites. And then once it got all the information, it did a re-ranking of which one was the best to answer the user's question. And last, I think this is the last paper I have up here. SireRag and Raptor. These are two papers that they received a lot of citations, and what their results were actually, they're pretty good. So they re-represented the data into clusters, or hierarchical clustering. So say you had, like this long document here, right? They told the model, they gave the model like chunks of the documents, and they said summarize those chunks. So now you have a bunch of these summaries of the different chunks. And then they did like a aggregating phase where they said which one of these chunks are similar and create a summary off of that. So they did that with, you have a bunch of summaries of summaries. And then they did, more steps until they got like a root node. And if you guys know computer science, instead of searching through an order of n documents, now you can search through an order of log n document, or however summaries were in there. So you start at the root node, and then you traverse down the tree to the bottom nodes that answer the user's question. I'm gonna skip that one. Okay, if you want to take a picture, this is the research papers. I recommend reading them. They're pretty interesting. Got it? Okay, these are some of my experiments, but we're running out of time. You guys can kind of get to know what this one is trying to say. So I did some experiments with like chunk sizes on the documents that I have. And even though I read all of those papers, of course, I had to do my own experiments because it's all different. But I get a general idea on what I could search for. Like I said, using the optimal chunk size is not greater than using more than the half of the context window of the large language model. So then maybe I would, not spend a lot of energy putting a bunch of documents or getting a large chunk size in there. And in this case, I tested chunk sizes from like 500 to 2000, and then, oh, this is the same image. Sorry, I thought this bottom was a different image, but they're the same. And here, the darker the color, the better the chunk size and the overlap. So for my documents, I would be using around 1500. And then this is plotting the chunk sizes. So the greater the chunk size, you go to the right, and then the higher accuracy, you get more accuracy when you go up. So as I increase the chunk size, my accuracy increased. And then I'm also doing stuff with knowledge graphs, which are pretty interesting. Okay, thank you all for listening to my presentation. I hope you all had something to learn out of it. And could I ask you guys to quickly fill out this evaluation survey on this workshop? Okay. If you have any questions, you can email me, tobalbar@hawaii.edu.
That's like what kind of costs are associated with using LLMs for that?
So are you using like APIs?
Yeah, if you want to use an API to like set up your own chatbot, like research organization.
Yeah, I guess it would depend on like how much people are using it. There's tools out there that do like an approximation of how much it would cost. But then, yeah, the only thing you can do is just have it running for a day, and then the API would just have a usage of all of that. But yeah, so you could do some experiments with like smaller models, just if you want to skip the cost, but you also have to validate it with the large language model. Yeah.
So the right in thinking that anytime you do this at the moment, you have to start from scratch, just about and implement the whole thing yourself, test it yourself. There are no
Special.
games that to start playing with this, at least in small scale, or
Not that I know of. Yeah.
because we have some ideas for some side projects that benefit from this. But my group was basically, I'm the software guy, and I already have a day job.
Oh,
Telescopes running as a business, like, yeah, good luck.
actually, if you can try to figure it out, I've been building, so this is open source. Yeah, so this GitHub is kind of like the template that I've been using for starting up these rack systems for my job. And I would just fork this repository, change, there's a like a config file in here. And then you can define like your collections, collection names, how you want to embed those documents that you have. But this isn't really like fully flushed out. Yeah, you could, I would say, maybe building your own would be faster. This is to give you an idea of how everything works. But stay tuned on this project that I'm working on. Maybe I'll get to a point where it's super generalized and useful.